Hello, welcome to the class. So today let's talk about cache a little bit more. So far we know we have virtual memory and our program, our kernel use virtual memory to manage this process. But actually, if you want to, the kernel want to run this process, it will load this virtual memory into your physical memory. And of course, because it's a memory hierarchy, so it will like keep uploading the load the data from your physical memory to your cache, to your maybe L2 cache, to L1 cache, then go to register, then compute it. So this is the kind of like memory hierarchy, and you just keep loading if the data is not in on your cache. Okay, so the cache is a very important component in here, and every time we try to compute anything, we will load the data into a cache because the register will use this cache data to compute uh, for your program, any like instructions. Okay, so let's see the cache a little bit more today. So you can imagine that in our physical memory, actually after you like load everything to a physical memory, there's a couple data here. Okay, there's a couple data here. Every time if our CPU, our registers want to get this data, you load this data into here, maybe L2, and you load data to L1, and you run it, right? But you will see there's a lot of like loading pace here. And because there's a lot of loading stuff. And usually when you run a program, for example, you define the two variable I and j. Usually you load A, you also load j later. So actually in this case, if you try to load the I here to here to here, then you try to load j here to here to here, then maybe you load k here to here to here. You will see there's a lot of loading here, right? So actually, when we define decide like how to do this cache model, how to load this data, we use a different way to decide. We try to package it as a block. So what's a block? Actually, we just try to get like a lot of bytes inside memory, and when we load it, we just load all byte here, then or load all byte here. So in this case, even we only need this one. This is the only one we need. We still load every data in the same block into the L2, into the L1, and use the data in here to compute it. The reason is why. The reason is that first one, if you only read one byte, you need to traverse a lot, figure out which byte you want to load, right? So it's take time. And after you load this byte, next time you load another byte, just closer it, which means you just need like a two different loading space, right? But if you can load like everything from the bottom to the top, and usually if your program has a good a design, you will reuse the variable again. For example, you will use for loop, nested for loop. You will use I and j again. I equal to 0, I plus plus, j equal to 0, j plus plus. You will use this variable, this like a memory space again. And usually they are close to each other. So if you can load everything in the same block into the next level, it saves a lot of loading time. Okay, so this is the idea. We use a block instead of like byte as a basic unit. The block is a basic unit about this loading process. If we want to load even one byte, if we have like 10 bytes in this block, but we only need one, we still load 10. Why? Because we believe in the future you will use other bytes in the same block. Okay, so this is roughly the idea of how to load in the data in your memory in your L2 and your L1. And what's the size of this block? Actually, there's a different strategy to define it, like how many bytes we want to it. And you will see something like a 4K bytes in a block. You will see something different, it's different in different cache. The L1, L2 use the same size of block, or L1, L2 use the different size of block. It can happen. So it depends on your design, your hardware design. You use a block instead of just use byte. So the memory address, we need to do a little bit trick. Why? Imagine that here, if your memory has like a 10, just 10 megabytes, and each one block is 1 megabyte. Okay, so each one block is 1 megabyte. You only have 10 block here in its memory, right? You can like separate 10 blocks. Okay, for 10 megabytes, this memory address, it's a huge number, right? But here you can only, for each block, they only need one address. So which means you only need 10 different address, not 10 megabytes different address. So which means we need to figure out a way to like simplify the memory address. Like if you give me a really, really long address, how I figure out like the address for the particular block. So this is the way to simplify it. How to simplify? Actually, you can use the block size. You can divide the block size to get the memory address. For example, if you have a memory address 0000001, 0000000, and 0000 blah, 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 the 10 and 11. Okay, so in this case, okay, so this is the memory address here, right? So imagine that there's a 4-byte here. Here is 4-byte. So assume one block equals to 4-byte. Okay, one block is 4-byte. In this case, if we want to get the block address, what's the common part? What's the common like bit for this 4-byte? Something here, right? Everything here is 0, 0, 0, and 0. So in this case, you know, if you want to get the block address, 0 should be the correct answer for this block address. So how we compute it? How we compute it? How we compute it? So actually, this is not so difficult because when you use the memory address, m divided by 4, you will get the same number here. This is 0, right? This is 1, this is 2, this is 3. 0 divided by 4 equals 0. If 1 divided by 4, 0. 2 divided by 4, 0. 3 divided by 4, 0. And the next block, you will see 0, 0, 0, 0, and 1, 0, 0, right? So for this case, because it's 4, so 4 times 4 equals 1. So it's going to give you a different block. So this block address is 0. This block is just 1. And so on. If you continue to do it, you will see still equal to 1. So actually, how to get this block address? You just divide by the block size. So block address of block address equal to the memory address divided by block size. So if right now the block size is 4K bytes, we can just divide 4K here. We can divide 4K here. We can divide 4K here. Okay, so this is how you get the block address. So you have this block address stuff. Right now, you can use this block address to figure out, okay, where's this block in the memory, right? So in this case, when we load the data, how we load this data. So let's see this example. Right now, we want to load this data, the first data here, and we try to load to L2. L2 has 3 memory chunks. So for example, this one is 10 megabytes. This one is 3 megabytes. This one is 2 megabytes. Okay, so you can see the memory in the cache, L2 cache. There's a 3 different area you can load this data to, right? You can put this data, let's say this data A. You can put this data A here. You can also put here or here, right? You can choose either one to load it. So which area you should load it? I think the next question is that which area in the cache table you want to load this data into it. Of course, after you load to L2, you also need to load to L1. And which location in the L1, you should load it. So this is the second questions we have, and this is the really critical part, and how we decide which area we want to load the data. So this example, there's a 3 different way you can load the data into your cache. So here, this is a cache, okay? This is a cache. And this is memory or lowercase cache. Might be the L1 here, L2 there, or this is cache, this is memory. Okay, so if you have these data, and right now we want to load, for example, data 1 to it. So which part you can put? So that's a 3 different idea. So I'm not going to tell you which one is the correct one, because there's a 3 different design. It's all about the architecture design, the device design. So I'm not going to tell you which one is the correct one. All these model can be used. So the first idea is, okay, think about that. These inside this memory stuff, this memory, you can imagine that each block is your team group. For example, if you have a team in your in this course, okay? So these team members, each team member is individual byte, and 3 or 4 student group as a block, as a team, okay? So right now, your team has a problem about your lab, and which TA you can ask for help? Actually, in this course, you can ask for any TAs, right? So, for example, this TA, you can just go to checklist. So we load the data to here. We can do it. Then we just make it flexible. If less data here, if less data here, you cannot go into the go to find the 学员数. You can go to find whole set, okay, or you can go to find the 清阳. Okay, so this is something like similar to what we have model right now. This model is flexible. It's full associated, so you can find any spot. If it's empty, you can just find it and go to put your data into the cache. So any single line here is okay for this loading. Okay, this model name is called fully associated. Fully associative cache. This is the first model we have. Fully associated. Every single spot you can just go in. Okay. So if this is not efficient, we have other idea to do it. And why? Why this is might not be efficient? Because first one, when you try to load in, you need to think about which block I should go in. So there's definitely an algorithm you need to compare. Okay, I check this one, check that one, check another one. You need to go through everywhere. So imagine that if we study, if we can study on the campus, and our TA's office is in different area in the campus, which means if you your team try to get one TA, but you find that the TA is already occupied by other students, and you need to move to far away to another building to find another TA. It's so inefficient, right? So same thing here. If you want to load the data, you need to check every single spot in the cache, try to find one. It's a little bit not so efficient. So that's another way to think about it. It's called direct mapped cache. So this is the second one. It's called direct mapped caches. So what's a direct mapped caches? The second idea is that, okay, I try to assign each team to a particular TA. So for example, if you are team group 1, every time you want to ask a question, go to particular TA. You just go to this TA. Other TA don't support you. Because in this case, your team know, okay, if I have a question, I just go there. I don't need to worry about other place. I just go there. If there's some student already be there, you can wait, or you can just kick out this team and try to occupy, like try to get the TA's help. So this is called direct mapping. For direct mapping, we have a like specific number to assign each block here. For example, the 0 should go to the 0, 1, and the 1, the block address 1 should go to 1, and 2, and 3. And if we got 4, we will go back to 1, and 2, and 3, and 4. Okay? Then we go to 1, and 2, and so on. So actually, you can see for each 4 of these, you try to match these 4, these 4, these 4. Okay? So this is called direct mapping. For direct mapping, we give you a site like a spot. If you have question, you have to go to the spot. So if we want to load you, you definitely need to go to particular spot. We already assume. If there's a data inside there, you just replace the data inside this spot. Just kick out the data and replace it. So this is another model. It's called direct mapping model for this like a cache loading stuff. This is the second strategy. Okay. So what's a potential problem for this? A potential problem for this is that if you get the case like okay, I try to load 0, then I load 4. So I come here is 0, then I replace it by 4, right? Then after that, I just go back to load 0 again. Then I just go to the 4. I always load the data from 0 or 4. I just ignore everything. In this case, you will find that even we have these bigger of your cache, you only use the first one and never use these 3. Because what? Because we have a direct mapping between these two data. We just keep loading 0, loading 4. We don't care others. So if this is the case, like by accidentally you only load these 2 blocks in your program, then you will see a lot of conflict. And even there's a lot of conflict, other 3 is still empty. So we have a different strategy between the first 4 associated cache and the second one, the direct mapping cache. We have a one, the third one, like kind of like the trade-off between these two. It's called n set n-way set associated. N-way set associated cache. Okay, so n here is a number. This number can be a pair, like can be how many block inside this cache I want to group together. So let's try, if we try to make this n, means we want to pair 2 block, two space inside the cache to be a group. So in this case, we try to group these 2 as a group, these 2 as a group, okay? So what's the idea of this? So because the student, if for example, always team 0 and team 4 has a problem, has a question, other TA feel like, oh, I don't have need to do anything, but the particular TA need to like handle a lot of like answers and questions, right? So we try to, in this case, we try to pair 2 TAs and here we try to pair each NTA, 2 TAs together as a group. So if you have a question, you just go to find this group of TA. Either TAs in this group can help you, okay? So still we use a mapping because we want to assign each student to find the right group of TA. So if you have question 0, you go to this group. If you have question 1, you go to this group. And the second one, you go to this group. This one, you go to this group. And 4th, go here, and 5, go here. So you can see we still assign each group into, we still assign each team into a particular group of TA. So the student, the team won't be like a trouble to find out like which spot it should go to. But also we have this pair of our spot, which means even though you load 0, then load 0 here, then you load 4 to here. 0 and 4 can be both inside this group because there's a 2TA, 2 spot for this data. Okay, so this is another way called two-way set associated cache. So if you got the idea, right now let's talk about how you get the spot, like which location in the cache you want to load your data into. If you have this like stuff. So let's see this example. If this is direct mapping, direct mapping means like for each one of these you should have a pair. You should just like assign it to the right spot in the cache, right? So in this case, remember this is a block address. This is not a memory address. This is a block address. If you have this block address, let's say B, how to get the spot? Actually, it's equal to B mod size of your cache, right? So here, the size of cache is size of cache equal to 4. So you just do B mod 4, then you will get the right spot on the cache to load this data into, right? Okay, so this is for direct mapping. So this is for direct mapping. But right now, let's see another way. If it's two set associated, if this is two set associated, how we change it? Actually, this is not so difficult, right? Two set associated means you have two group. You have 48, you pair each two, so you only have two groups. For these two groups, how many groups you have? How many groups you have? When you have this group, you will see the first one will go here, the second one will go here, the third one will go here. So actually, this is still B, mod what? Not the size of cache. We change it to the size of groups, number of groups, not size of groups, number of groups. So you can see actually we can change it a little bit. It will say number of groups. Okay, number of groups. If you see number of group here, you can change it for equal to 2. Okay, so how to get the number of groups? If it's direct mapping, number of groups equal to size of cache divided by 1, because each one in the individual spot is a group. If you try n-way associated, for example, it's 2, then you should change this number to 2. Of course, if it's 3-way, you should change it to 3. So this is how you get n for this number. So this is actually the n here. B mod n, and n is what? N is equal to the size of cache divided by how many group you have. How many group member in each group you have, okay? So if you have two set associated cache, which means each group has 2 TA, each group has 2 spot, then you divide by 2. So in this case, size of cache is 4. 4 divided by 2 equal to 2. So you have 2 groups. Of course, if you want to make a group of 4 set associated cache, then you change this to 4, which means everything here is one group. And the n will be equal to 1. So in this case, everything mod by 1 equal to 0. So if everything mod by 1 equals to 0 means every this block can go to any single spot in the same group, because everything here is a group. It's the 4 associated. Okay, so 2 associated means this number equals 2. 3 means 3. 4 means 4. 4 associated here means this number equal to the size of cache. If this number equal to size of cache, this is 4 associated cache model. Okay, so that's a couple way to look at, and this can help you to get what's the address you should load the data into in the cache. Okay, so today's lecture is really important because today's lecture we covered actually the basic concept about the cache placement, how to place the data from the low level memory stuff to the up level. If we have to like load the data, we load it as a block, not a byte. We load a block of like a lot couple bytes into the next level of your memory hierarchy systems. Okay, and when you load the data, which spot in the high levels memory device you want to load into, there's a three different strategy you can use. There's a full associated cache. There's a direct mapped cache. There's an NSET associated cache. So with different strategy, the spot you want to load into your data will be different. Okay, so this is kind of the roughly idea, the basic idea how to like load the data from the low levels memory hierarchy to the higher level one. And we will cover more details like in the next videos. Okay, so hope you enjoyed today's video. Okay, so see you next time. Cache placement is awesome.